So another type is the common emitter and bypassed emitter resistor single power rail, and the configuration looks as follows. We got VCC, we got RB1, RB2, got the transistor, we got RC, we have RE, then we've got ground. We also have the input is applied on the amplifier through the base, of course, through a collector capacitor. You notice that we don't put VS and RS anymore because we know how to move from VS to VI. But when we load the input side, that means we are adding RS and VS. Right. On the output side, we also have is taken from the collector because it's a common emitter. We observe the input side and the output side from the emitter. See you there. Got V out where we could also load it with RL. DC analysis, this time I'll not go back into this. The point is that RE is not bypassed, and in fact, even in terms of AC analysis, I would like you to actually attempt it on your own before you carry on with this video, but I will provide it now. But I highly encourage you to attempt it on your own because it's the same principles, knowing that a cap behaves like a open circuit in DC and a short circuit in AC. So now DC analysis, as I mentioned, we've covered. In terms of AC analysis, by the way, in terms of the DC analysis, the caps will behave like open circuit, which means the RS part and the VS will be cut out in the analysis. But in the AC analysis, caps behave as short circuits, which makes now VS come back basically through RS to get to VI, and that VI cap behaves like a short circuit. Now voltage, DC voltage sources behave like ground, so RB1 is suddenly in parallel of RB2. We enter the transistor through its base, IB is flowing there. The small signal equivalent circuit of a transistor, it's NPN, so VB, EO, V pi, it's the same thing, through R pi, across R pi, caused by IB flowing into R pi. We reach the emitter where IE flows down, and as we reach the emitter, there's no capacitor at the emitter, so we've got RE present, we go to ground, we got on the collector side, it's NPN, so IC is flowing down. IC is equal to GMV pi. We still have RO, the internal output resistance. We got IC flowing through RO and RC basically, because we as we go from the collector, we also have RC all the way to ground. Then we've got V out that can be loaded in some conditions depending on what type of load we're looking at. We've got our VI point, which is that point, and our V out point. In terms of VI, we've got R in, which is the input resistance as measured from that point to ground, which would be nothing as RB1 in parallel of RB2 in parallel with R pi plus RE times beta plus 1. So there's similarity with the double resistor single parallel, which is the very first one we studied. Just that here we've got a single resistor, which is RE. The other one we had two, of which one became obsolete in AC analysis because it was bypassed by cap. R out is still the same, RC in parallel of RO. Ideally, R out ideal, of course, is just RC, because R out is equal to infinite in that case. The unloaded gain AVO is V out over VI. IC is still of opposite direction as to IB, so that will be my net beta IB, which is IC basically. times R out divided by V in, which is the same voltage, the same voltage. Since we don't know the current through there, we don't know the current through there. So VI is still the same here, but we know the current through there and there. We're going to use that part of the parallel network to define VI, which will be R pi IB plus REIE. And of course, IE being equal to beta plus 1 IB, we can put IB as a common factor, we get R pi plus beta plus 1 RE. Because IE is beta plus 1 IB, so IB can cancel, we left with minus beta R out divided by R pi plus beta plus 1 RE. So if once more we get beta R out divided by, if we put R pi as a common factor, we get 1 plus beta plus 1 R pi RE. Beta over R pi is GM, so that will be minus GM R out divided by 1 plus, if beta over R pi is GM and beta is quite big, beta plus 1 is almost approximated to beta, so that will also result in beta plus 1 to be more or less GM RE. Now this is something very similar to double rail, and we have covered that already. The half loaded as well as the fully loaded can follow. A quite different type of common emitter circuit is the double parallel one, meaning there's not just VCC, there's also VEE. And what changes most here is mainly the DC analysis. So, but let's look at it. The common emitter amplifier, double power rail, bypassed RE. The circuit looks as follows: VI, CI, got RB to ground. We have the base, the emitter, RE, which is bypassed by cap, of course, CE, all the way to ground. And this side we've got VEE, which is another power supply, that I was saying double power rail. Got RC on this side, and we've got VCC, which is the other power supply. C out, the output is taken from the collector once more. The input is coming through the amplifier through the base, and we observe everything from the emitter. That's what makes it common emitter. And the output is taken from the V out. It could be applied to a RL, it could be loaded. The input side could also be loaded through RS and a voltage source VS. Okay, so as I said, the biggest change is basically the DC analysis. Of course, in the DC analysis, capacitors behave like open circuits, making that part being cut out, as well as that part, as well as that part. So we are left with just RB to ground. Then we've got the base, got RE to VEE. Then on the other side we've got RC to VCC. That's what is left of the circuit, because the caps behave like open circuits. So how do we do the DC analysis of this? You'll recall that for this diode to be forward biased, there must be a higher voltage potential here compared to there. Since ground is the highest side on the base side, which is 0 volt, that means VE must be a negative value. It must be a value lower than 0 volts. So it must be maybe minus 12 volt, minus 5, but it's a negative value. So to do the analysis, we're going to have IB flowing there from high voltage potential, which is 0, towards a negative voltage source. If we consider this loop there, Kirchhoff voltage law will give us, as we go from 0, well, minus 12, because must be equal to RB times IB, because that's the current that flows. IB is the current that flows through RB, plus VBE plus REIE. So that leads to 0 minus VEE basically. 12 was just an example. So that will be minus VEE equals to RBIB plus 0,7 plus RE times beta plus 1 IB. So IB equals to minus VEE divided by RB plus minus VE minus 0,7 divided by RB plus RE beta plus 1. Right. So those two. But now remember, VEE, as we've established for the EBJ junction to be forward biased, must be a negative value. So if that is negative, then minus VEE is actually a positive value. You agree? Greater than 0, positive. Okay. Yeah, that's how we get to that. And remember here, when I say 0 minus VEE, I just applied Kirchhoff's voltage law that you must have learned in electrical engineering. Okay, basic electrical engineering. And now we move on to the AC analysis part. But before we do, because once we get IB, you can get IC as beta IB, of course. You can get IE is IB plus IC. You can get, very important is that you can get VRC, which is the drop across RC, as RCIC. How do you get VCE? You now consider the other Kirchhoff's voltage loop, which is all the way from VCC to VEE. So there, it's VCC minus VEE must be equal to RCIC, ICRC plus VCE that we are looking for plus REIE. All right. That being said, you can extract VCE from here as being VCC minus VEE, which when V is negative, you're gonna end up being VCC plus minus VE. So if let's say VCC is 12 and VE is minus 12, so that will be 12 plus minus 12, which is 12 plus 12, which will be 24 basically. All of that minus RCIC minus REIE. So that would conclude your DC analysis basically. Now, how do we proceed for AC analysis? For AC analysis, the double rail ends up becoming more or less like the other cases we've studied with bypass CE, because the DC voltage sources, of which we've got two here, VCC and VE, will become ground. Capacitors behave like short circuits, so which brings back VS, RS, of course, VI. Then caps is there as a short circuit. We've got RB going to ground. Then we enter the transistor, fruit base, we've got IB flowing there. Got R pi, got plus minus V pi. Then we have it's NPN, so GMV pi parallel with RO. Then we've got the emitter here, and as we go to the emitter, we're supposed to have RE, but now the capacitor behaves like a short circuit. RE all the way to VE, which becomes ground. Capacitor becoming short circuit all the way to ground. 0 ohm in parallel with RE, so that capacitor will bypass RE. So we're gonna end up becoming having that emitter just grounded. And on the other side, we've got IC, of course, opposite direction to IB still, and we've got RC connected there. We reach our output point from where we observe our R out to Z out. the input point here, we observe our Z in or R in, the same thing. And we could have a loaded case, in which case we have RL connected. And this is very similar to something we've already analyzed. Okay. So we can also have the common emitter double rail, but which is unbypassed. And that's the note on page 5. The common emitter amplifier notes take you through that. Highly encourage you to analyze it and derive the formulas as well. It's going to be very similar. The DC analysis is what changes a bit. Actually, it's going to be the same as what we just did now. But in the AC analysis now, since there's no bypass capacitor anymore, we'll just have RE. RE will be present now on the emitter, and we know the implications of that. Okay, very good. Yeah, and the other one is the common emitter double rail amplifier with no RE at all, and the analysis is similar. So I'd like you to play around with that and derive the different formulas. You should be able to get the same formulas as the ones in the note. Okay. So now we move on to a different configuration that is called the common base amplifier.